Hello viewers, welcome to this lecture on kinematics model for robot manipulators. So in this lecture we will see how coordinate frames can be assigned at every joint of a robot manipulator. So in the last lecture and the previous lectures we have seen how the position and orientation of one object with respect to another can be expressed in the form of homogeneous transformations or a 4 by 4 matrix form. So in this lecture we will see how such coordinate matrices can be assigned at each joint, and finally how to obtain the arm matrix of a robot manipulator. If we consider a robot manipulator, model like this, the base and various joints are given, and this is the end effector of the robot manipulator. Now if the robot has to handle an object in its workspace, then the robot should know the whereabouts of the objects. In other words, it should know the position and orientation of a particular object so that it can handle the object in a comfortable orientation or position. So how to obtain the position and orientation of the object with respect to the end effector, because end effector has to handle that object. In many times we may be knowing the position and orientation of the object with respect to the base of the manipulator. So we should be able to convert that information with respect to the end effector of the manipulator. So in total what we want is, we want to find the relation between the base of the manipulator and the end effector of the manipulator, as well as with the object in the environment. So for doing this we should know, or we should attach various coordinate frames, and the position orientation will be expressed in terms of homogeneous transformation as we have seen in the previous lectures. So first, if we have a coordinate frame at every joint in a particular manner, so we can, and if we call this as the base frame B and this is the end effector frame E, then if we write B T E, that is the end effector frame with respect to base frame, this will be a 4 by 4 matrix. In this, the first 3 by 3 matrix represent the rotation or the orientation of the end effector with respect to the base coordinate frame, and the last column we can call it as the vector P represent the position of the end effector. In other words, the origin of the end effector coordinate frame with respect to base coordinate frame, how far it is away from the base coordinate frame, that is the position of the end effector. So if we know the position as well as the orientation of the end effector with respect to base, that will give a picture, a correct picture of a robot manipulator. So 0 0 0 1, because as we have already seen, now the steps to find the kinematics equation for a robot manipulator is as follows. We assign the Dinavet-Hartenberg coordinate frames at the joints of the manipulator, and then after assigning the coordinate frames we define the link parameters, link and joint parameters, joint and link parameters of the robot manipulator, and then we find the transformation matrices between two adjacent joints. Finally, we find the arm matrix. This arm matrix is nothing but the relation between the end effector and the base of the manipulator. This BTE is called the arm matrix. So, if a manipulator is given, a particular structure is given, then we can find a unique arm matrix, which is the relation between the end effector and the base frame, by following these 4 steps. So, first let us see what is the DH procedure, Dinavet-Hartenberg procedure. So, first we have to assign the numbers for the joints. So, we can call this as the first joint is the base, that is 1, then 2, 3, 4, the end effector is 5. In this particular picture we say there are 5 joints. Now, for each joint we establish the coordinate system in the following way. First, we want to establish a right hand coordinate system at every joint. So, for the base frame, the base of the manipulator, first we assign a coordinate frame. How to assign? First thing is we have to assign the z direction of the coordinate frame. So, every manipulator, as we have seen in the introductory lecture, there are 2 types of joints, that is revolute or prismatic. So, the prismatic joint means the sliding joint, and the revolute joint is a rotational joint. So, let us assume that the first link is a revolute joint. The first joint is revolute and the axis of rotation is this one. So, we call this as the Z0 axis, as given in this step. Second step, Z0 is assigned to be the axis of the joint. Then we can assign the x0, y0 arbitrarily so that it forms a right hand system. So, we write x0 and then y0, and so we can observe that x0, y0, z0 forms a right hand system. Then we go to the next joint. So, how to fix the z axis of the next joint? So, that is also the axis of rotation or the axis of sliding, whether it is a rotational joint or prismatic joint. So, let us assume that the second axis is also a rotational joint, where the rotation is performed in this way, that is perpendicular to the paper. So, this is the Z1 axis. So, once we fix the two axes for the 2 joint, the first joint Z0 is fixed and the second joint Z1 is fixed here, then the origin can be fixed suitably for the second joint. The origin is nothing but the intersection of the Zi minus 1 and Zi. So, they are intersecting at this point. So, we call this as the origin O1, because it is the first joint has origin O, the second joint we call it as O1 and etc. The ith joint, the origin is called OI minus 1. So, how the origin is fixed? It is the intersection of Zi and Zi minus 1. Now, if let us say the third joint is also a revolute joint. For example, let us say Z1 and Z2 both are parallel. So, here also there is a rotation about the Z2 axis revolute joint. Then how to fix the origin at this joint? So, it is given by this expression. If the Z2 axis and Z1 axis are intersecting, then the point of intersection is called the origin. But if they are not intersecting, then the common tangent, common normal between the two Z axis where it intersect at Z2 is called the origin. So, we can say that O2 is the point of intersection of Z2 and the common normal between Z1 and Z2. So, it is given here, the origin of this is fixed in this way. So, if they are not intersecting, then Zi with the common normal between Zi and Zi minus 1 will be the origin of the system. So, whether the two Z axes are intersecting or not intersecting, this procedure can be followed to fix the origin of the coordinate frames. So, once we fix the Z axis for various coordinate frames, various joints and the origins for those joints, then what we can fix is the x axis, establish the x axis at each joint. It is given by the vector perpendicular to both Z I minus 1 and Z I. So, the xi vector is the vector perpendicular to both Z I minus 1 and Z I as given in this. But if the Z I minus 1 and Z I they are not intersecting each other, then we can take the common normal as the x axis. So, here if they are parallel or non-intersecting, then the common normal between these two axes will be the xi axis of the system. So, once we fix the xi axis and already we fixed the zi axis, it is easy to fix the y axis to form a right hand system. So, in this way we can fix all the coordinate frames at every joint of the manipulator. Now, if we have the end effector of the robot manipulator is a special joint. Here there is neither rotation or translation because it is at the end of the manipulator. So, we have to assign a coordinate frame without considering the revolute or prismatic joint. So, what we do is we take the vector perpendicular to the end effector, the wrist of the manipulator, that has the z axis, and the vector which is joining the two fingers of the end effector as the y axis, and the x axis can be fixed as a to form a right hand system. X, y, z should form a right hand system. So, the z axis at the end effector is called the approach vector. So, z axis is approach vector, okay, and then the y axis is called sliding vector, sliding direction, and x axis is fixed according to the right hand system. So, this will complete the fixing of coordinate frame at every joint of a robot manipulator. So, using this coordinate systems, next we can find the relation between the ith coordinate system and the I minus 1th coordinate system. So, we want to see. So, now we give the coordinate system as x0, y0, z0 is the base coordinate system, xi, yi, zi is the ith coordinate system. I is equal to, we can have 0, 1, 2, 3 up to n. Nth coordinate system is the end effector coordinate system. So, by DH procedure we have already fixed this coordinate system. Now, we want to find the relation between the I minus 1th system with respect, the ith system with respect to I minus 1th coordinate system. So, I minus 1 Ti, it represent the homogeneous transformation between ith and I minus 1th coordinate frames. So, the joint coordinate frames, how they are related, that is what we want to see. So, for doing that we have to define the parameters at every joint. So, there are 4 parameters theta I, di, alpha I and ai. These 4 parameters to be fixed at every joint. So, theta I is called the joint angle and di is called joint distance, ai is called the link length and alpha I is called the link twist angle. So, these 4 parameters, some of them may be 0 and so we can fix the 4 parameters at every joint by following these definitions. So, here first thing is we have to locate the point bi, which is the intersection of the axis xi and zi minus 1. Because we have already fixed all these coordinate axes, the intersection of xi and zi minus 1 is called bi point. If they are not intersecting, then the common normal between xi and zi minus 1 with xi wherever it is intersecting, that is called the point bi. Then define the angle theta I. The joint angle theta I is defined as the angle between xi minus 1 and xi axis, these 2 axes which is measured about the zi minus 1 axis. So, if you have zi minus 1 axis, so for example, if you have in this particular picture, we have z0 axis this way and x0 axis is here. Now, we can fix by following this fixing of xi axis, this one, it is the vector perpendicular to z0 as well as z1. So, we can say that this is the x1 axis, z0 and z1, the perpendicular line is either in this direction or in the opposite direction. So, we can select any one of the direction, but it is a convention that we select the direction which is pointing towards the end effector of the manipulator. So, we call x1 axis to be this line. Now, the theta 1, how to define theta 1? It is the angle between x0 and x1. If we put I equal to 1, so x0 here and then x1, the angle between them measured about z0 axis. So, how this x0, it rotates about the z0 axis, so that x0 and x1 are parallel. So, that angle is called the theta 1 angle. Similarly, all other angles, if you take x1 and x2, the angle between x1 and x2 measured about the z1 axis will give theta 2 value. So, etc. If it is a revolute joint, then the theta is variable. If it is a revolute joint. Okay. If it is at a revolute joint. Now the joint distance di, it is measured from OI minus 1 of the ith frame to the point BI. So already we have defined what is BI. So if you want to calculate D1, the joint distance D1, we have to see O suffix 0, that is the base coordinate frame's origin and the point BI, B1. So the distance between them measured along Z0 axis will give the value D1. Similarly, D2, D3 all can be measured using this expression. And the link length AI, it is a distance between the point BI and the origin OI. And similarly, the twist angle alpha I is the angle between the axis Zi minus 1 and Zi measured about the vector xi. So these 4 definitions for the parameters of a robot manipulator at every joint is given by this procedure. So once we have this definition, then we can construct the matrix, the relation between one coordinate frame with the other coordinate, that is ith coordinate frame with respect to I minus 1 coordinate frame. So we can see from this picture, at every joint we are fixing a coordinate frame suitably, x0, y0 is at 0, x1, y1 is at 1, etc. Now how to relate one coordinate frame with the other, that is to be seen in this expression. So if we have the base coordinate frame like this and another coordinate frame to be like this, and the third joint has a coordinate frame this way and the end effector coordinate frame is this way. So we can have the 0th frame and then first frame, second frame, etc., the nth frame. We want to find the relation between the first frame with respect to the 0th frame, and then we want to find the second frame with respect to the first frame. Similarly, we want to find the nth frame with respect to the previous frame, n minus 1th frame. So if we have all these relations 4 by 4 matrices, then if you multiply all this, so we can see that the relation between the nth frame with respect to the 0th frame can be obtained. As we have seen previously, we can multiply successively. If you are doing a homogeneous transformation successively with respect to the current coordinate frame, we should multiply in the right hand side. So by that logic, we can multiply all this matrix one by one, and then finally we get the relation between the end effector and the base as 0 Tn. But how to find this 0 T1, 1 T2, or in general how to find I minus 1 Ti for the ith frame with respect to I minus 1th frame. So for that we use the 4 parameter definition as given here. So we can see that, for example, theta I, if we take this one, if we take the base frame Z, the x0, y0 is at 0 and x1, y1 is at 1. If we make a rotation by an angle theta 1 about the z axis, then we can see that x0 and x1 will become collinear, they become parallel. So if we perform a rotation here we can see that we perform the rotation about zi minus 1 axis by an angle theta 1. What we see is the x0 axis will become parallel to x1 axis. Similarly, if we perform rotation about z1 by an angle theta 2, then x1 axis will become parallel to x2 axis, etc. So, first we concentrate on, let us say, this 0th axis and the first axis, x0, y0 is at 0 and x1, y1 is at 1. So, first if we make a rotation about z0 by an angle theta 1, the x0 will coincide with, not coincide, it will become parallel to x1. Now, the second step, if we make a translation of the distance d1 along the z direction. So, translation 0 0 d1 along the z direction if we take. So, if we take along the z direction d1 distance, then we can see that this origin will coincide with this origin and the x0 axis already has become parallel to x1, it will exactly coincide with the x1 axis. So, that is the performance here. We make a translation of 0 0 d1 so that x0 axis will become coincide with x1 axis. Now, if we make again a translation of a1 0 0, that is along the x direction a1 0 0, then we can see that the origins also will coincide. The origins O0 and O1 will also coincide, and if we make a rotation about the x axis by an angle alpha I, then the z axis which are different, in this case we can see z0 is pointing in this direction, z1 is pointing perpendicular to the paper. So, they will also coincide if we make the twist angle alpha I rotation about the x axis. So, we see that after making this 4 rotation and translation, 2 rotation and 2 translations, the base coordinate frame x0, y0, z0 completely coincide with x1, y1, z1 coordinate system. So, that means we have obtained 0 t1, the first coordinate system with respect to the 0th system after making these 4 operations. How we have made this 4 operation? First a rotation, then translation, again a translation and then rotation. If we multiply 4 of these operations like this, one by one whatever we have performed, then we get a matrix, this expression. So, this expression contains theta I and di, alpha I, ai, all the 4 parameters are involved. So, this gives the relation I minus 1 ti. Okay, so, it should be expressed like this. The relation between I minus 1 ti is given by this. So, this we will explain using a concrete example in the next lecture to obtain the ARM matrix of a robot manipulator. Thank you.